All right. Well, how about this? When we're looking to find a multiplicative inverse, what we have to do is we have to actually first go out and determine, are the two numbers relatively prime? So what does it mean to be relatively prime? Okay. The remainder of what is 1, Omar? What do you mean the remainder is 1?
In order, if they're relatively prime, that means that the only common factor between them is 1.
Right. The greatest common factor, the GCF,
Mhm.
for the two of them, or the GCD of A and B has to equal 1. It's exactly right for them to be relatively prime. Okay. So for two numbers to be relatively prime, their GCD has to be equal to 1. All right. So what we're going to do first is we're first going to go out and find a GCD. Let's say, for example, I want to find the GCD using the Euclidean algorithm. Okay. Find the GCD of 73 and 27. So go ahead and do that. Let's take a minute to do that. Use the Euclidean algorithm to find the GCD of 73 and 27. So we'll start with that. I'll give you, let's say 2 minutes. It's about right. No problem, Luis. Oh, no problem, Hans. Okay, so let's go through and do this. right? So we're going to start out. We've got 73 is going to equal 27 times 2 plus 19, right? Because it's 54 plus 19, that's going to give me 73. Okay. Then what I'm going to do, I've got 27 and 19. So 27 is going to equal 19 times 1 plus 8. And then 19 is then going to equal 8 times 2 plus 3. Then we'll have 8 equals 3 times 2 plus 2. And then 3 will equal 2 times 1 plus 1. And finally, 2 will equal 1 times 2. Okay, which means that my GCD there, okay, after I finish my Euclidean algorithm, the GCD of 73 and 27 is going to equal 1. Okay, now for us to find our multiplicative inverse, the next thing that we've got to do is we need to now find the linear combination of 73 and 27 that gives us 1. Okay, so that's going to be 73 times some number A plus 27 times some number B is equal to 1. And if you remember, we're going to utilize, right, each one of these equations inside of our Euclidean algorithm. So you go ahead, I'll give you a couple of minutes to do that. Remember, as a hint, you're going to start from the bottom. So we're going to start from the bottom. Okay, so what we're going to do now, next piece we have here. So we've gone in, we're now finding the linear combination. So we've got, what we want to do is we want to start with this bottom one because it's going to end up being equal to 1. So we've got 3 minus 2 times 1 equals 1. And so that's our first equation. And then what I'm going to do is I'm going to actually plug in, I'm going to rewrite the second equation up from the bottom. I'm going to rewrite it 8 minus 3 times 2 equals 2. And then I'm going to see, okay, I've got a 2 here in my equation. So this is 3 minus 8 minus 3 times 2 times 1 equals 1. And so that gives me 3 minus 8 times 1 minus 3 times 2. And that's going to equal then 3 times 3 minus 8 times 1 equals 1. So that's my second equation. So now I'm going to go one up, okay? And my next one up is going to be 19 minus 8 times 2 equals 3. Okay, so I've got 19, right? This one here is 19 minus 8 times 2 equals 3. And so I'm going to put that into here. And so that is going to give me now 19 minus 3, excuse me. Sorry. Yeah, 19 minus 8 times 2 times 3 minus 8 times 1 equals 1. So this is 19 times 3 minus 8 times 6 minus 8 times 1 is then going to equal 1. Or another way to write that is 19 times 3 minus 8 times 7 equals 1. Next one up is going to be then 27 minus 19 times 1 equals 8. So I'm now going to replace 8. So I've got 19 times 3 minus, okay, and it'll be 27 minus 19 times 1 times 7 equals 1. We'll rewrite that one as 19 times 3 minus 27 times 7 minus 19 times 7 equals 9, or plus 19 times 7, excuse me, plus equals 19 times 10 minus 27 times 7, and that equals 1. Almost done. I've got just now my last equation right here that'll end up giving my linear combination. And so my linear combination now is going to end up being, or we're now going to substitute 19. So it's going to be 73 minus 27 times 2 times 10 minus 27 times 7 equals 1. So this is going to end up being then 73 times 10 minus 27 times 20 minus 27 times 7 equals 1. And I can rewrite this, and I'm actually going to take out the minus sign. I'm going to make it a plus. I'm going to write it as 73 times 10 plus negative 27, or excuse me, plus negative 20 times 27 equals 1. Right? And so, yeah. And if I can also just rewrite this just to make it very clear. 73 times 10 plus 27 times negative 20 is going to equal 1. So now I have my linear combination. Go ahead and write that down. Make sure that you have that process. It could take a minute or two. Probably the longest process that we have instead of the entire exam, instead of anything that we're doing right now. You with me so far, Carlos?
Yes.
Awesome. Oh, you were totally right. Yes, it's 27 and 27. Got my numbers. So this ends up being negative 27 and 27. Yeah. Thank you, Van. I was just, when I went through, I went too quickly instead of adding together the 7 and the 27 and the 20. All right, great. So now, one of the things that we want to do now is to just note, okay, now we can find our inverses. The linear combination actually gives us our inverses. All right. So the inverse, and what you want to notice here, okay, is be very, very, very aware, very cognizant. The inverse of 73 mod 27. So that's 73 over here, and then we're going to go mod 27 is going to be here, is going to be 10. Is 10. Okay? So it's the A value that goes next to 73 in the linear combination. Then the inverse of 27 mod 73, and notice we just flipped the values, all right, is negative 27. But I'm going to rewrite that as a positive because we don't write inverses as negatives, all right? We don't want a negative inverse. So, okay, what we'll do is we're going to write the equivalent in positive terms of negative 27. And the easiest way to do that is to just subtract. Take 73 minus 27, okay? And that ends up equaling 46, okay? And it turns out that negative 27 mod 73 is congruent to 46. So 46 is your is congruent to 46 in mod 73. So 46 is the inverse of 27 in mod 73. So once we've gotten there, then it's just a matter of figuring out which one it is, okay? It turns out 73 times 10 mod 73 is 0 because it's 73 times a number. 73 times any number is always going to be 0. 27 times negative 27 in mod 27 is going to be 0. So what that means is that you're just left over with 1 every single time. All right. And that's what it means to be an inverse. Okay. So to be an inverse, of A, B must fulfill the following. A times B mod M must equal 1. That's what we're basically saying. A times B is mod M is going to equal 1, and hence it makes it an inverse. An inverse. So let's just prove that. We'll take 27 times 46, and we'll take it mod, right? Mod 73. Okay. I go in and I check. That's going to be equal to 1,242 mod 73. And that is equivalent to 1. Or actually, we'll write this 1242 mod 73 equals 1. You can go and check yourself too. Use either the division algorithm. Yeah, use the division algorithm. And we'll do the equivalent. Go ahead and check then for, go ahead and check for 73 and 10, right? Show that 73 and mod 27 has an inverse of 10. And that's just a check. You can either, like I said, use your calculator or use the Euclidean algorithm.
Daddy, where's Mommy?
I don't know, honey. I'm teaching. I'll be back in a second. 1 minute. 1 minute.
I need to do this.
I'll be on. It's okay. Okay. Just hang out. Just hang out. 1 minute. So 73 times 10, right? Mod 27 is equal to 730 mod 27. Okay. So what we end up with is 730. We can just see if you want to go to the Euclidean algorithm, or excuse me, the division algorithm method is 27 times 27 plus 1. Okay. So 10 is the inverse of 73 mod 27. How's that, Carlos?
Yeah, that's better. I got it.
You got it? Okay, cool. Anybody else have any other questions about that one? Great question. Something that's going to show up. It just kind of like brings in a lot of different skills that are actually going to be end up being on that exam. So yeah. It's to do algebra, actually, to do algebra mod, anything. So for example, let's say, for example, that I had, that I wanted to do this. What is 73x? 73x is equivalent to 7 mod 27. Okay. See how that works? Now, I want to find x. And the thing is that sometimes what we're trying to do is we're trying to actually find an unknown for a lot of different reasons. From a math perspective, it's just that we want an algebra. I want an algebra. I want to be able to do algebra. I want to be able to like do algebra sometimes. So I want to find x, okay? And the way that I'm going to do that is I'm going to do this. I'm going to take 73 times 10, x, or rather I'm going to take 10 times 73, I should say. Multiply both sides by 10, so that'll be 10 times 7, mod 27. And so we know that this is equal to 1. So this is 1x equals 70 mod 27. Okay. And if I take 70 mod 27, that's equal to 16. So x is congruent to 16, or actually x equals 16. So that's actually how you go out and solve equations modulo whatever number that you have. In some cases, you can't solve, okay? But in this case, because we have an inverse for 73 and modulo 27, we can solve. What do you think, Mon? Yeah. So like, for example, I'll give you another example here. In some modulo, there are very few inverses, like 4. Modulo 4, you got 1, 2, and 4. I mean, like, well, because 2 doesn't have an inverse. 1 and 3 will have inverses. 12 is another one where a lot of the terms you have in 12, right? Because 12, if you look at 12, 12's factors are 1, 2, 3, 4, 6. And then we also have ones that have common factor like 8, okay, 9, 10, and 12. So that they all share factors. So they don't have necessarily. Now, in some cases you do. They don't have inverses. Mod 12. I just don't. They're like, in some cases, they're like 0, right? And in algebra, we call them 0 divisors, right? Where you actually multiply by a number and you get back 0, which is weird. But in other cases, right? Or let's say, for example, for m equals 7, every number other than 7 has an inverse. And I'll show you. We'll do a little table. Has an inverse because 7 is prime. So if we construct a table, right? We got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? So this is a multiplication table. For 7, every element is relatively prime. And so we got 1 times 1 is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? That's just 1 times each one of those numbers. Still going to be 1. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 1. So you can see that the inverse of 2 is 4, and the inverse of 4 is 2. I'll say that in just a second, okay? Because when you multiply 4 times 2, you get 1, okay? 3 times 2 is 6. 3 times 3 is 2. 3 times 4 is 12, and 12 is equivalent of 5. 3 times 5 is 15, and that makes that 1. So 3 times 5 is 1, and 5 times 3 is also 1. Okay, then we go to 6, or we go to 4 now. 4 times 6, that's 24. So 24 is equal to 3 modulo 7. 4 times 3 is 12. So that ends up being equal to 2, right? We had that before. 4 times 4 is 16. So that's equal to that's equal to 2. 4 times 3 is 12. 12 is actually equal to 5, pardon me. 4, 8, 4 times 2 is 1. That's right. This is 1. Because 4 times 2 is 8, and 8 is 1 modulo 7. It totally starts at 0 to 6. Just treat this as 0. Fine. I forget our book does it that way. All right, so and then we take 5, and we know that we've got 5 times 3. We know that 5 times 3 is going to end up being 1, because 3 times 5 was 1. Okay, and now we go to 6, right? And if we look here, 6 times what is going to be equal to 1? Yeah, 6 times 6. 6 times 6 equals 1, right? Because 6 times 6 equals 35, and 35 is congruent to 1 mod 7. The demonstration here is to show you that in the case of prime numbers, every number is actually relatively prime. So every single number is going to have an inverse. Okay, and so consequently, in mod 7, we can do division with any number, or we can do any kind of algebra that we want, as long as we're not multiplying yep, that's right. We can do algebra with any number that we want, as long as it's not a multiple of 7, because then you'd end up just be multiplying by 0, right? So in that case, we might do something like this. We might say, okay, well, 5x is equivalent to 11 mod 7. And in this case, we'd see 5 and 3 are, right? Because 5 times 3 is going to end up giving me 1. So I'll take this, I'll make this 3 times 5x is equivalent to 3 times 11 mod 7. So x will end up equaling 30, or be equivalent to 33 mod 7. So x equals 5. And there you go. And as we said, that is the purpose of doing that kind of stuff. It is pretty neat. Yeah. All right. Let's take 5. So let's be back at 221. Okay. Let's be back at 221. We're going to go over and do some more integer representation stuff. Let's take a look now some at integer representation, unless people have other things that they'd like to look at the moment. But let's look at, I particularly want to be transforming into some new bases. And so let's start out with, I want to, let's suppose I want to write B3A base 13 in decimal. Okay, so I want to do B3A base 13 in decimal. How am I going to do that? Any ideas? I'm sure you guys actually have a pretty good idea, right? What do you think, Vin? How am I going to do this? B3A.
E equal 11 multiple
B equals 11. Okay, great. Can you speak up just a little bit, Vin?
3 equal 3, A equal 10.
Okay, 3 equals 3 and A equals 10. Great. And so what are you going to do with those?
11 multiple 13 square
Great.
plus 3 multiple 13 plus 10.
And we're going to say 10 times 13 to the 0th power. Awesome. Great,
Yes.
great job. Thank you, Vin. And so this is then going to be 11 times 169 plus 3 times 13, and then just plus 10. So this is the 0th power of my base. This is the first power of my base. And then this is the second power of my base. So we're just going to take that many, right, and multiply each one of them by each one of our terms. And I got 1908. There we go. Awesome job, man. All right, let's try this one out on your own, everybody. Let's do in decimal. When you're done, put your answer in the chat. Great. You got it, Eats? Oh, okay, got it. You're checking yours against it? Okay. All right. So what we've got here is we've got 5 times 8. Well, actually, I'm going to go from the 0th power. I like to start from the 0, like go from the right-hand side. So I've got 0 to the 0th power. I'm going to have 2 times 8 to the 1st power, plus, and then 0 to the 2nd, 0 to the 3rd. So then this is going to be 5 times 8 to the 4th. So 5 times 8 to the 4th plus 2 times 8 to the 1st. Okay. Gotcha. It is going to be 20,496. And there we go. All right. So just be careful with those. Any questions on that? So that's transforming one in what's it called? In a different base into decimal. Let's go the other way around. Let's go from decimal into a different base. And in this case, we're going to use the Euclidean algorithm in order to do this. Okay. So let's say, for example, I have n equals 91, right? Okay. And I want to turn it into base 3. So what I'm going to do is I'm going to use, the division algorithm. I'm going to just divide out. Okay. I'm going to divide out, and at each step of the division algorithm, that's going to end up giving me each one of my place values. So I'll take 91 is going to equal, and that'll be 30 times 3 plus 1. 30 times 3 plus 1. And so I'm going to imagine, I'm going to put down my parentheses there. So my ones digit is going to be a 1, right? And it's kind of thing you want to kind of think about why it is the case, because it's kind of a cool idea, right? It is basically, I've just peeled off all the digits, all the things that are less than 1. Now I'm going to go take my Q, my quotient, 30, and that's going to equal 10 times 3 plus 0. So my remainder is now going to be the next value my next decimal value, 0. Not decimal value, next place value, 0. Then I'm going to take, right? Okay, so what's basically happened now is I peeled off all the powers of 3 that were in 90, right? That were not some other power of 3, and there just aren't any. So there you go. So now I got 10, and 10 is going to equal 3 times 3 plus 1. So there's 1. Now I got 101. And then I'm going to take 3, and 3 is going to equal 3 times 1 plus 0. So there's a 0 right there. Okay. And then finally, I've got my 1. And so 3 equals 1 times 3. And we're done. Brain fart. This is, I've got 10, and that's my 1. And then I have 3. 3 equals 3 times 1 plus 0. Right, okay. And so now we end up with, 3 equals 3 times 1 plus 0. And then finally, that is our last value. There's the 1. There's our question. Yeah. So this is 1 times 3 to the 4th, and we're done. Good. And you can check, this is 81 plus 0 plus 9 plus 0 plus 1. And that is 91. All right. Let's do another example. Let's do 171 in hex. So we'll have n equals 171, and we'll do it in hex. And so that means base 16. So I've got 171 is going to equal, it'll be 16 times 10 plus 11. Okay. And so my first term here is going to be an 11. And so 11 is going to be what? That's going to be a B. That's going to be B. Then we'll have 11 is going to equal, and 16 is going to equal now, excuse me, not 16. 16 times 10. 10, right? Okay. Well, we're pretty much done. 10 is actually less than 16, so we're finished. So once Q is less than, okay, our base, we are finished. All right, and so 10 is A. So 171 is actually AB. There you go. And we can look, see that that's the case. So A is 10. 10 times 16 to the 1 plus 11 times 16 to the 0 is equal to 171. All right, and so that actually, that's why that ended there too. I had just forgotten, right? Q is now less than 3. So we're done. All right, let's try it again. let's try it with, you guys try it out with n equals 840. And my base is 9. When you have it, put it up in the chat. Why don't you check it, Adam? You should be able to like go turn it back into decimal, and when you turn it back into decimal, it should be 840. All right, good deal. I think you got a typo there, Eats. You can't have the left hand term can't be a 0. The other thing that I would tell you too there, Utes, is that if we're in base 9, the value has to be bigger than if it was in base 10. The digits have to be large. There have to be more of them, or they have to be larger. You kind of think about it, it's because each digit we can't go as high. So 103 is actually less than 840. That's how you know it's not 103. So we'll start out, we've got 840. Okay, and that's going to end up being 9 times 93 plus 3. That's our first one. Excellent. Second one now, we're going to go 93 is going to equal 3. And so first term is a 3. Second term, 3 times 31, right? Plus 0. There's a 0. And then we'll have 31 is going to equal 3 times 10 plus 1.
Professor, shouldn't it be 3 times 10 plus what? Or 9 times 10 plus 3 for 93 is equal to, because we're on base.
Oh,
9,
it's base
correct?
9. Yes, you're right. It's base 9. God, goodness gracious. Yes, absolutely. 9 times 10, thank you, plus 1. And well, that keeps it as a 1. But now I've got 10 is going to equal 9 times 1 plus 1. And so there's my 1. And then notice
the remainder for 93.
Huh?
It's a 3 as a remainder for 93.
Oh, yes. Thank you. Let me start over. 840 is equal to 9 times 93 plus 3. Okay, so that's going to be my 3, excuse me, my first 3. And then 93 will equal 9 times 10 plus 3. And so 3 is my second term. And then now we've got 10. So 10 is going to equal 9 times 1 plus 1. So there's my 1. And then finally, right, 1, okay, is now less than 9. So that's going to end up being my, oh, excuse me. Yeah. So the 1 is going to end up being my last place value. So we get 1, 1, 3, 3, base 9. Yes. Right? Okay. If it's clearer for you, Mon, I just know that that's when I end my loop. I end my loop when Q is actually less than 1, and I just make that equal to my last base. So what Mon is saying is, can we just say, oh, isn't it 1 equals 9 times 0 plus 1? And the answer is yes. So then you just make 0 your last term. Or not 0, but then 1, your remainder, ends up being your last value. There's the 1. The difference here, well, yeah, I guess that's the difference here is that we're going to keep actually, instead of putting in the difference with that one, Mon, I would say is that you're putting in R instead of Q. So you're actually shifting what the value is that you're putting in for the place value. So I don't know. There you are. If we look, right? Oh, well, actually, there it is. That's actually good. 1, 1, 3, 3. That's good. 1, 1, 3, 3. There it is. We'll do that. That's fine. All right. This thing doesn't stop. I'm gonna kill it. I swear I'm going to kill my computer. All right. Let's take a look. It just shows up. It hasn't showed up in the entirety for 2 years. I've never seen it. Showed up today. All right. Here we go. Let's take a look. Let's now actually, what we want to do now is we want to shift to, we want to translate. We've got this one that's going to be in hex. We'll translate hex into binary. Okay. So we're going to translate hex into binary. And so what we're going to think about when we translate hex into binary is each hex term is 4 binary terms. Okay, so let's see what this means. It's something along the lines that it looks like, say, for example, I have 1 FC. Okay, so I've got 1 FC. And so C in hex, let's just rewrite these, what these values are in decimal. So 1 is 1. F, right, is 15. Okay, and C is 12. Right? So we look here and we got 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So now I just need to write each term in binary. So 12 in binary, right, is going to have, well, we can actually just do this. We'll take it 12 is equal to 2 times 6 plus 0. Okay, so that's 0. You know what? Now that I'm thinking about it, I like Mon's way of doing it. So 6 is going to equal 2 times 3 plus 0. 3 is going to equal 2 times 1 plus 1. And 2 is equal to oh, excuse me, and 1 is equal to 2 times 0 plus 1. And so there is our binary G, 1, 1, 0, 0. And that's what 12 is, or that's what C is. Okay, so C is equivalent to this one. All right, and now we'll go in and let's do F. F was 15. So we'll take 15, and 15 is going to equal to 2 times 7 plus 1. And then we'll have 7 is equal to 2 times 3 plus 1. And 3 is equal to 2 times 1 plus 1. And 1 is equal to 2 times 0 plus 1. So F is 1, 1. I need this one actually. 1, 1. It's 1, 1, 1, 1. Base 2. Base 2. And finally, we need 1. Okay. Now, here's the thing about 1. Right? 1 is just going to be 0, 0, 0, 1. Okay. 0, 0, 0, 1. And so in binary, if we were to do all 4 of them, 0, 0, 0, 1, base 2. But notice that it's the furthest left over. Okay, so it's the furthest left value. And so consequently, what we're going to get here is we're going to get, we don't need the first 3 zeros. So those first 3 zeros aren't going to actually be necessary. So all I'm going to do is I'm going to have, right, this is going to be the furthest over right because it's C. C is the furthest right. F is the next furthest over, and then 1. So we're just going to put those in that way. And so this is going to end up being 1, 1, 1, 1, 1, 1, 1, 0, 0, base 2. And that's going to be equal to 1 FC in hex. Okay, so what you'll do is you'll reinterpret each hex term into decimal and then transform it into binary, right? And we'll just do it by, there'll be sets of 4, right? First 4, second 4, and then finally the third 4. Questions on that? Okay. Let's actually go the opposite way around and let's convert from binary to hex. Okay. So let's convert from binary to hex. And let's say, for example, we take something that looks like this. I got 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1. And that's in base 2. And what I want to do is I want to convert it to hex. So to do that, I'm going to split it up into pieces of 4, or into parts of 4, chunks of 4. Because remember, each 4 different hex, okay? And then what I'm going to do is I'm going to take those and I'm going to turn them into some value in hex. So like, for example, if I have 0, 1, 0, 1, that's the first term, okay? That's going to be my furthest right hand term when I turn it into hex. So 0, 1, 0, 1 is going to end up being 2 squared plus 2 to the 0, okay? Which is equal to 5. Then I'm going to move over 1. And then 0, 0, 0, 1. Well, that one's pretty simple. That's equal to 1. That's 1 in base 2. Or 1 in base 16, excuse me. Then I go to 1, 0, 1, 0. All these in base 2. And that's going to be 2 cubed plus 2 to the 1. And so that's 8 plus 2, and that equals 10. And in hex, that's A. So that'll be A. Then I'll move over 1 to 1101. In base 2. And that'll be 2 cubed plus 2 squared plus 2 to the 0. So that's 8 plus 4 plus 1. That's going to be equal to 13. And 13 is D in base 16. And then we'll have just 1, 0 in base 2. And 1, 0 is simply 2 to the 1, which equals 2 in base 16. And so there it is. 2DA 1, 5 in base 16. Questions? Good to go. All right. So, anybody else, anything that you want me to go over right now? Okay. So here's what's going to happen on Tuesday. Thursday is our exam. So Thursday is the exam. Okay. On Tuesday, I will once again make class optional. It's totally up to you as to whether or not you want to come or not. What I'll do is I will be here. And if you have any questions that you want to go over, anything from the homework, anything as you're studying, please feel free to come on in, ask any questions that you have. Otherwise, if you want to study on your own, go ahead and study on your own. Okay. So that will be next week on Tuesday. Thursday is the exam. Please be here on time because you're going to have an hour and a half. The exam will open. Okay, the exam is multiple choice. It's in Canvas, so it's going to open at 1:40, right on the dot in which we start, and then it will close promptly at 3:10. Okay, make sure that you have some paper and that you have something to like actually use in order to upload your exam as well. Not your exam, but like your scratch work, because for about I think 6 or 7 of the problems, you'll have to show your work and upload your work, and there'll be an upload section for that. Okay. Okay. All right. Well, great job today. Have a great weekend, you too. And I will see you on Tuesday or on Thursday. Have a great one.
Have a good weekend, Professor.
You too.
Have a good one, Professor.
You too, Hans. Bye, Len. Adios, Mom. All right.